Good day. My name is Kishen Mewalall, student number 55896758. In this presentation, I will discuss my TPG3700 design project for the proposed upgrade of Alma Road near Waterberg Estate in Limpopo. This a surveyor from Limpopo gave me this data which I've used in my project. The project deals with upgrading the existing rural road corridor to a surfaced 4-lane divided road. I use Civil Designer Student version 9.1 as the main geometric design software, and the report also includes a manual horizontal curve calculation and Excel curve calculation tool, a TRH4 based pavement design, conceptual drainage, earthworks, and the final drawing evidence. I'll keep the presentation focused on the main design decisions, the software outputs, and the engineering reasoning behind the choices made. The first point is the project. The assignment required a complete road design report and a set of software generated drawings. The road had to be an actual road, and the final alignment had to be between 4 and 5 kilometers long. The brief also required the use of geometric design software, not only manual sketches. For the calculation part, one horizontal curve had to be calculated manually and then repeated using an Excel sheet. The pavement design had to be based on TRH4, which alternatives considered before selecting a final pavement structure. The project also had to include stormwater drainage with actual chainage locations, earthworks, and mass haul output from the software itself, and drawings showing the plan, long section, cross sections, drainage locations, markings, and signs. So the presentation follows that same order. The road selected for this project is Alma Road near Waterberg Estate, west of Modemole in Limpopo. I chose this road because the route could be viewed in Google Earth. This is my Google Earth image there, and my two chainage points. And there was also usable survey and road information available in Civil Designer, which was given to me, that made it a practical route for doing a software-based design. The surrounding area is mainly rural, with open land and scattered properties and hilly terrain. Because of this, the road is suitable for a geometric design project because the alignment, vertical profile, drainage, and earthworks all become important. The existing road is treated as a rural gravel road corridor. Upgrading it to a surfaced divided road improves riding quality, reduces dust and loose gravel problems, improves wet weather access, and gives a stronger pavement structure. After coordination in Civil Designer, the final road one length is approximately 4.299 kilometers. For the design basis, the proposed road standard is a surfaced 4-lane divided road. This means 2 lanes in each direction with central separation between opposing traffic streams. The upgraded road is treated as a rural mobility route with a minor arterial function. I did not treat it as a freeway, but the divided layout improves safety and capacity compared with the existing gravel road. A design speed of 80 km per hour was adopted as per the TRH. This was also selected because the route is in rolling to hilly terrain and follows an existing corridor with several changes in direction. A much higher speed would require larger radii, more sight distance, and more earthworks, while a lower speed would reduce the operational standard. The prelim cross-section includes 3.5-meter lanes, shoulders, a central median, crossfall, and open side drainage. The main software workflow was completed in Civil Designer. The first step was to open the available survey corridor and confirm the road position, which I've done. The horizontal alignment was then coordinated as road 1 with the final chainage running from 0 plus 000 to 4 plus 298, which is 0 to 4.298 kilometers. After the alignment was set up, the profile and edge level information were generated and the road template was applied. Cross sections were then extracted and drawing sheets were generated. The software was also used to calculate the earthworks and mass haul output. This workflow is important because the project is not only a written report. The design had to show software evidence, and Civil Designer provided the plan view, long section style output, cross-section drawing sheets, road template output, and volume calculation evidence. For the geometric design, the horizontal alignment was kept as close as practical to the existing road corridor. This helps to limit unnecessary deviation from the current route while still allowing the road to be upgraded to a 4-lane divided standard. The alignment includes several changes in direction, which is expected because the route passes through rural and hilly terrain. One of these curves was selected for the manual horizontal curve calculation. The vertical alignment was based on the available Civil Designer survey levels. The long section style output is included in the combined drawing sheet. The vertical design is treated as prelim because in a full professional design, it would need further refinement to improve the cut and fill, balance, etc. One horizontal curve was selected for manual verification. The selected curve is the third main curve along the alignment. It was treated as a simple circular curve. The adopted radius was 300 meters. The deflection angle was 28 degrees, 55 minutes and 9 seconds. And the PI chainage was 3 plus 389. From the manual calculation, the tangent length was calculated as 77.36 meters. The curve length was 151.42 meters. The external distance was 9.81 meters and the middle ordinate was 9.5 meters. The beginning of curve was calculated as 3 plus 311 chainage, and the end of curve was calculated as chainage 3 plus 463. These values were then repeated using the Excel curve calculation tool. The Excel output matched the manual calculation apart from the normal rounding, which confirms that the spreadsheet can be used again for similar horizontal curve calculations. The evidence of this is within my report. The cross-section and drawing output was one of the main parts of the software evidence. Cross-section sheets were generated from Civil Designer at 120 meter intervals. This is also found in my report. The drawing set includes the early chainages, middle sections, and the end of the road at approximately chainage 4 plus 299. The report includes representative cross-section figures in the body, and the drawing annexures includes the generated cross-section sheets. The cross-sections showed the relationship between the existing ground line and the proposed road template. This is useful because it shows how the proposed road fits into the existing terrain at regular intervals along the alignment. The combined Road 1 drawing also includes the plan and long section style output, so the drawing set covers the main geometric design outputs required by the brief. For the pavement design, the TRH4 catalog method was used as the basis. No traffic count, axle loads, survey, or lab test results were available, so the pavement design had to be based on clear assumptions. The adopted road category was category B. The assumed design traffic class was ES3, and the structural design period was taken as 20 years. The subgrade CBR was assumed as 8%, but it was treated conservatively as a 7% catalog support condition. The selected pavement structure consists of 40 mm of asphalt surfacing, 150 mm of G1 crushed stone base, 150 mm of C4 cemented base, 150 mm of G7 selected layer, and 150 mm of ripped and recompacted in situ material. The assumptions are acceptable for this assignment design, but we will need to confirm in the full length design. But for now, they are acceptable. Three pavement alternatives were considered before choosing the final structure. The first option was a granular-based pavement. This option was selected because it is practical, flexible, uses conventional road building materials, and is generally easier to maintain. The second option was a cemented-based pavement. Although it provides good stiffness and load spreading, it can be more sensitive to shrinkage cracking and reflective cracking. The third option was a hot mix asphalt-based pavement. It can give good performance and riding quality, but it is normally more expensive and requires more asphalt production and construction control. Based on constructability, maintenance cost, and expected performance, the granular-based pavement was the preferred option for this prelim design. Proper drainage and compaction control remain important for the final pavement performance. The drainage design was treated as a conceptual stormwater layout. As you can see, my changes for the drainage are there, but actual drainage points positions were still provided. This was important because the brief allowed hypothetical drainage sizes but required actual drainage locations for the drainage facilities. The proposed drainage system uses road crossfall to move water away from the travel lanes. The shoulders then assist with moving runoff towards open side drains. Cross drainage is provided by proposed culverts where stormwater needs to cross the road alignment. The main culvert locations identified were chainage 2+778, chainage 3+309, and chainage 3+465. These positions were selected from the Road 1 alignment using the point chainage information and visible low or crossing areas. Scour and silting were also noted because culvert outlets must discharge water without damaging the side drains, shoulders, or embankment slopes. The earthworks and mass haul outputs was calculated in Civil Designer using the road cross-section data. The existing ground was taken from layer 1 and the design cross-section from layer 2. The volume calculation included a topsoil stripping depth of about 0.2 meters and roadbed preparation depth of 0.2 meters. The software calculated an unadjusted total cut of 66.162 cubic meters, 66,162 cubic meters, and an unadjusted total fill of 4,661,219 cubic meters. After the adjustment for compaction and topsoil stripping, the cut available for fill was 3,352 cubic meters, and the fill shortfall was 4,657,867 cubic meters. This shows that the current design is fill dominant. In a detailed design stage, the vertical alignment should therefore be reviewed to reduce imported fill while still keeping acceptable gradients and drainage. The final submission evidence includes the main civil designer drawings and supporting outputs. Drawing 1 is the Road 1 combined drawing, which shows the coordinated alignment, road list table, chainage information, and long section style output. Drawing 2 includes the cross-section drawing sheets generated at 120 meter Intervals. Drawing 3 includes the earthworks and mass haul output from civil designer. Drawing 4 shows the drainage facility locations with their changes. Drawing 5 shows the conceptual road markings and sign details, lane lines, edge lines, median side marking, 80 km per hour sign, curve warning, etc. This report also includes proof of access to Civil Designer Student version 9.1. This evidence supports the software use and drawing requirements of the assignment as per me. This is all found in my report. To conclude, this project covered the main geometric and pavement design requirements for the proposed upgrade of Alma Road. The coordinated alignment length is approximately 4.299 kilometers, which falls within the project brief. Civil Designer was used to create the software-based road alignment, combined drawing, cross sections, earthworks, and mass haul output. One horizontal curve was calculated manually and then checked again using Excel. My Excel's tool is in my report. The pavement structure was selected using the TRH4 catalog approach, with the granular base pavement chosen as the preferred option. The drainage design include actual drainage positions for the proposed culverts. The design remains prelim, and a full professional design obviously would require traffic surveys, geotech testing, hydro analysis, etc. Thank you.